For part D, we're going to be starting with what we used in Homework 1 Part B, which is our CSTR, which shows us our concentration and temperature with all of these starting values. And what we're going to be doing is splitting this up into 20 smaller CSTRs in order to simulate a plug flow with. Why am I speaking like a fucking idiot? For Homework 1, Part D, what we're starting with is a copy of our Homework 1, Part B, which has a lot of these initial values, which we're going to keep the same. But what we're going to be doing is splitting this up into 20 different reactors. So if we do that, we need our actual volume and total volume to be different things. So we'll remove this. So our total volume is 100 liters, which means our volume is going to be our total volume divided by the number of tanks we have. Make sure to run these. So instead of 10 minutes, our simulation is only going to be 2 minutes this time. Our initial temperatures are going to need to be changed because there are going to be 20 of them now. And so we'll start with that. So our T0 is going to be our NP.full. We want N, and our value is going to be 338.5 degrees Kelvin. And then our CA0 will be the same thing, NP.full over our initial concentration is going to be 0.5 molar, and we want there to be n number of these. So we'll combine these two terms into our initial vector, so vec0, np.r underscore, and then we want we have CA first already, so we'll start with CA, and then we'll have our T0 second. So now we have a vector of both our CA and initial temperatures. And lastly, what we need to do is change our incoming temperature. So our new temperature that will be coming into our first tank is going to be 338.5 kelvins, and that will be constant. So now we're going to be using some of the ideas from part C, where we had the tanks flowing into each other in order to calculate that. So for this, we're going to need to split our vector back up into our T and our CA. So P dot split our vector, and we'll split this into two different ways. And one thing that's important to note now is that since our T is different for each tank, our T will be changing, meaning our K value will also be changing. So our change in concentration is this, what we have here. However, this is going to be our first tank, since what we learned in our last part C is that our first tank is going to be a little different than the rest of the tanks in series, which will be equal to our CAN, which is always going to be equal to 1 in this case, minus our concentration going out of tank 0. So we have our CA, and we want CA0, so this will calculate our change in concentration of the first tank. Now we also want this to be our initial K, so K0, and then again our CA0. So this is how we will be calculating the change in concentration of our first tank. It's important to note that our flow rate and our individual volume, which we just counted for, is going to be the same. So now dc concentration dt for n tanks is going to be equal to our flow rate divided by our volume times we need our, so what's going into the next tank and then out of that tank. So what's going into our second tank is going to be our concentration, but the first one. So what's coming into our second tank is the first concentration. So we need 0 all the way up until our very last one, which is done like so. And then subtracted from that will be our concentration. And then we'll start at our second one, and then that will go all the way to the end. So our last tank will be subtracting out. This also needs to account for our concentration and our K value. So K1 all the way until the end multiplied by our CA1 all the way until the end. So these two equations should give us our changing concentration of each tank. Just double checking, making sure everything looks alright. I don't see anything that immediately sticks out. So we'll continue on to our changing temperature of our first tank. So dt 0. QV isn't going to change. Our TI is going to be a constant, but now our initial T is going to be equal to 0. And then our K is changing again, so we need our K0. Concentration's changing. CA0. Rho and C are constant. Again, this T0 because our T is changing. And then our TC, our cooling temperature, should not be changing, so that can stay. So that's our first tank. Now, for every tank after our first, it's going to be our T from the very first one all the way to the second to last, or our last tank, and then subtracted from that is going to be, so we have what's coming in from our first tank, which is T0, and then we'll be subtracting T1 from that all the way up until the very end, which will give us the changing temperature from tank 1 in our list to, in reality, all the way up until the end. So again, our K is changing, but in this case it's going to be K1 all the way into the end, CA1 all the way until the end, and then temperature 1 all the way until the end. And then from this, we are going to want to return R and P dot R underscore list, and then we're going to want to keep this in order. So we have dCA dt0. We want dCA dTn, dC or dt dt0, and dt dtn. We need to change this to n. So now we should have a list of all of our concentrations from the first to the last, and from the first to the last temperature. So what we need to do to update our solve IVP, so it's still right hand side, 0 to T end is now 2. This we can call our Vec0. This might need split. Continue for now. It seems to have worked. I want to check. So what's our, so we can have our CAs and our T's. This is going to be P dot split of our res dot sol of our T plot, and then this needs to be split into 2. So do we have our T plot's down here a little further. So we'll see if that causes any issues. Seems to be okay. So let's see, our CAs seems to be alright. And our T's looks pretty alright. Okay. So go back here. And then what we're going to need to do next is add our figures for each thing we're looking for. So are going to be our temperatures and our concentrations. So we're going to need to add a line for each tank. So we'll have our figure, rows 1, column 1. So for I in range n, so for each tank, we're going to add a figure. Add scatter. Our x is going to be our t-plot. Our y in this situation is going to be our CAS. However, we want this to be, so we have our CAs and then our times. So we're going to want our CA of I, and then for every single time. And then this is going to be in row 1, column 1, and we'll give this a name, which is going to be equal to, we'll call this our CA for the I that we are using. So CAI. And then we'll do the similar thing for temperature. We'll copy this. So for I in range n again, we have our time, and then we want this to be our t's. And then instead of CA, we'll just call it T. This is in row 1, column 2. And then we want fig.update layout. So hopefully this works. Wow. After a little bit of investigation, something looked a little off, but I couldn't tell what it was at first. I did miss one single letter, which is dividing our heat transfer coefficient over the number of tanks we have. So that should change our results slightly. Yeah, so what that was doing was it was making it seem as if much more of the heat was getting transferred out than there really was, which was resulting in why our temperatures and reaction rate were dropping so much for each tank. So this is what the corrected looks like, which looks much better. When you zoom out and take a bigger picture look at the 10-minute interval rather than the 2, you can see when the system of our 20 reactors in a row, simulating our PFR, kind of come to a steady state. So as you can see at the beginning, they all start at 0.5, and the ones near the end that are not being supplied with the 1 molar concentration liquid are slowly decreasing in concentration, and the reaction rate isn't happening very quickly, which is why the temperature of these is also decreasing. However, once that concentration spike reaches these, the concentration is slowly increasing, and in turn causing the amount of reaction happening to increase, which therefore increases the temperature, as it is an exothermic reaction. And as this temperature increases around here, this is what is causing these to come back down. So when the reaction rate increases, the temperature increases, which also causes the reaction to further increase. So it's kind of a positive feedback loop of higher temperature, faster reaction, more temperature. But once it gets to a certain concentration, there isn't enough to continue that positive feedback loop because of our cooling water, which is why that eventually they come to a steady state. And as you can see, that they don't all come to a steady state at the same temperature, which is due to the fact that they're not all at the same concentration, because although the reaction is not in a positive feedback loop causing it to go all the way to zero, some of it is still reacting, causing heat to be expelled from the reaction. And this reaction is also causing the concentration to slowly decrease as it moves towards the end of our reactor. So these two reasons are the reasons at why it doesn't all just converge at 1 molar, and why the temperatures come to different steady states for each part of the series. Okay.